Hi, today we're going to be doing Unit 10, Section 1. This whole unit focuses on acids, bases, and solutions. So today we're going to start with a basic look at what solutions are, how do ionic compounds behave in water, and the such. This is all the things that you're going to learn today in this lecture. So a solution, like we saw at the beginning of the year, is a homogeneous mixture where you have usually solid dissolved in a liquid. There are other kinds of solutions. You can have a gas dissolved in a liquid as well. But for the most part, we're going to be focusing on homogeneous mixtures where a solid dissolves in a liquid and you cannot see the difference, therefore the word homogeneous. So you cannot see the difference between the solid and the liquid. It looks like one liquid usually. The components are not chemically combined. They return the original properties. And so this is not a compound because we're not combining, we're not bonding any of those chemicals. We're simply dissolving one chemical in another. A very perfect example of this is sugar water or salt water. Sugar water still tastes sweet just like the sugar does, even though the sugar and the water are mixed together. It retains properties of both the water and the sugar. Salt water still tastes salty like the salt originally does. And we can separate that by boiling the water away, and then we'll get either that sugar or that salt back. That makes it a mixture because it's a physical process, not a chemical one. A solution is usually made up of two chemicals, and we call one the solute and the other one the solvent. A solute is the chemical that we dissolve, whereas the solvent is the most abundant chemical, the one that is usually doing the dissolving. So in the previous example we had of salt water, for example, the salt, the sodium chloride, would be the solute, and then the water will be the solvent. Most solutions that we see in honors chemistry are going to be solutions where the solvent is water, because that is the most common solvent that we use in chemistry, especially for inorganic chemistry. A solute in these cases is usually going to be a solid, although a solid could also be a gas or a liquid. But in most cases that we're going to see, the solid is going to be a solid. Now, remember from one of our earlier units that the term aqueous is used for whenever a solution has water as its solvent. So most of the solutions that we deal with in this class are going to be aqueous solutions where water is our solvent, our most abundant component that does the dissolve. Now, solubility is one of the key features of solutions. Solubility refers to the maximum amount of solute that can be dissolved in a particular solvent at a specific temperature. Now, in everyday life, we see this a lot. For example, you're making iced tea and you put sugar in it. Once you put too much sugar in your iced tea, it stops dissolving. The sugar stays solid. And that's because that solution of sugar in the tea has reached its solubility, has reached its maximum. After we have reached the maximum amount of solution, that that solution or the maximum amount of solvent or solute in the solution, that solution will no longer be able to dissolve. So that solute will no longer be able to dissolve, and we'll get a solid staying in there. Now, there are three kind of different words that we can use to describe how much of the solute is in a solution. We can use the term saturated here, and the term saturated is going to mean that we have no more solute that can be dissolved. We have reached the maximum amount of solute that can be dissolved. So that's the term saturated here. And the term unsaturated means that more solute can be dissolved, so we haven't reached the maximum yet. In a saturated solution, we have reached the maximum. In the unsaturated solution, we have not reached the maximum, and so we can dissolve more and more solute. So basically, you can think of saturated solution like the iced tea. Once you have added too much sugar and the sugar stops dissolving, the unsaturated solution, it will be when you first start putting sugar in the tea, and as you add more sugar, that sugar keeps dissolving because it has not reached maximum yet. And then a supersaturated solution is a special circumstance. A supersaturated solution is a solution which is holding more of that solute than it should theoretically be possible, meaning that that solution is holding more solute than it should. And there's really only one way to make a saturated solution, or sorry, supersaturated solution, which is to heat up a solvent, make it saturated, put as much solute as we can possibly put in there, and then slowly cool it down. As we slowly cool down that saturated solution at a higher temperature, it becomes super saturated because a hotter solution can hold more solvent. As you are probably aware, hot tea can hold more sugar than cold iced tea, and that's because of the temperature difference. So if we make a saturated solution at a higher temperature and then we slowly cool it down, we'll get a super saturated solution. And I'm actually going to show you a video of this. I'm going to put it separately on Schoology so you can watch this video, which we'll see later is going to show that that supersaturated solution. I will put this video on Schoology so you can watch it separately apart from this lecture, and so you can see how a supersaturated solution looks and how it behaves. So what factors affect solubility? We already spoke about one factor that affects solubility. Solubility is affected by temperature, and that's how we use temperature to make supersaturated solutions. Most solid substances are going to have a higher solubility as the temperature increases, which means that if we have a solvent and we heat it up, if it's at a higher temperature, that solvent will be able to hold more solid. That's why we can then cool down the solution and then make it supersaturated, because that extra solid doesn't come out of solution right away. Now, gases are the opposite to solids, though. If we're dissolving a gas, if we have a gas as a solute, gases have lower solubility as temperature increases. If you took marine science or environmental, you're probably aware of this, because as the oceans get hotter, as lakes and rivers get hotter, as temperature goes up in the world, less and less oxygen, which is a gas, dissolves in that water. And therefore, fish die because they need the water dissolved in, or the oxygen dissolved in the water, etc. So solids and gases have opposite solubilities when it comes to temperature. Solids, the higher the temperature, the more they dissolve, whereas gases like carbon dioxide, like oxygen, the higher the temperature of the solution, the lower their solubility is, the less they dissolve. The other thing that will affect solubility can be pressure. Now, pressure only affects the solubility of gases. Pressure does not affect the solubility of solids, only of gases. And gases are going to become more soluble as that pressure goes up. And you can think of a bottle of soda, like Coca-Cola, Fanta, Sprite. If you think of a bottle of soda, that bottle, when it's first closed, when you first buy it, has a really high pressure. That's why when you look at a bottle of Coke or you look at a bottle of Pepsi, there's doesn't look to be any bubbles. But the minute you open it and you let the pressure out and the pressure drops, then you get bubbles of carbon dioxide, because the carbon dioxide becomes less soluble at that lower pressure. So gases are going to have a higher solubility at higher pressures, whereas the pressure will not affect the solubility of a solid. Now, liquids. When we make a solution out of two liquids, we use a bit of a different wording. A liquid solution will be something like putting isopropyl alcohol in water, or putting acetone in water when we are mixing two liquids. When two liquids are mixed, we don't call it a solvent. We don't call it dissolving, because dissolving is a word that we reserve for solids. When we are mixing two liquids, we use the words miscible and immiscible. The word miscible means that two liquids will uniformly mix together, meaning that they will actually mix. Milk and water is an example, isopropyl alcohol and water is an example. any two liquids, and when you put them together, you can't tell the difference between the two, they mix together. We call those miscible liquids. On the other hand, immiscible is the opposite. Immiscible means that two liquids will not mix together. They will form two layers. Oil and water is the most common example of this that you have been listening or hearing about since elementary school. When you mix oil and water, they separate and they form two individual layers. They do not mix together. So we say oil and water are immiscible. As a general rule in chemistry, we can say that like dissolves like. And this is referring to intermolecular forces of the two things that we're trying to either mix or dissolve. Nonpolar with nonpolar things will mix together, so they will be miscible. So for example, if we try to mix gasoline and oil, both gasoline and oil are nonpolar molecules, and so they are miscible. Whereas if we try to mix a nonpolar and a polar compound, they will be immiscible. For example, oil, which is nonpolar, and water, which is polar, will be immiscible. Gasoline, which is nonpolar, and oil and water, which is polar, will be immiscible. On the other hand, again, it's like dissolves like. So if two things are polar, they would be miscible. So for example, if we try to mix isopropyl alcohol, which is polar, with water, those two would mix together. Those two would be miscible. Same thing with most of the parts of milk and water will be miscible. So whether two different liquids can mix together or not is going to depend greatly on their polarity, which we learned earlier in the year. If two compounds are polar, then they will mix together. If the two compounds are nonpolar, they will mix together. But if they're different, if one's polar and one's nonpolar, or vice versa, they will not mix together, making them immiscible. Because again, as a general rule in chemistry, we say like dissolves like, and that's referring again to intermolecular forces. Now, if you remember though, intermolecular forces only account for covalent compounds. So what happens when we have a ionic compound? Something that is not covalent, like sodium chloride, like salt in water. When we're mixing ionic compounds in water, it's a different type of behavior. Ionic compounds don't just dissolve in water, they do something we call dissociate. When an ionic compound dissolves in water, the ions don't just stay together as sodium chloride or whatever ionic compound you have, they actually dissociate, which is what we're seeing here in this picture. Essentially, when we have a big ionic compound, we studied ionic compounds earlier in the year, and we saw that ionic compounds are made of these big crystals made of repeating negative and positive ions. The polar water molecules, which have a partial positive and a partial negative, with the water being, or the oxygen being partial negative, the hydrogen being partial positive, are going to be attracted to those ions. When we have a positive ion like this one, the oxygens, which are partially negative, are attracted to that positive ion. So when we have something like sodium chloride, that sodium ion in sodium chloride, Na+, gets surrounded by water molecules with the oxygens, which are partially negative, pointing at that positive ion. On the other hand, the negative ions, like the chloride ions in sodium chloride, are going to be surrounded by water molecules because the polar water molecules are attracted to them, with the hydrogens that we have down here facing the chlorine or chloride ion, the negative ion. Because the hydrogen ions in water are partially positive, so they are attracted to the negative ion. The process of these ions being ripped apart from the crystal and being surrounded by water is called dissociation. The process of those ions being surrounded by water specifically is called solvation. So dissociation is the breaking apart of the ionic compound into ions. The process of solvation is the surrounding of the ions by water molecules. So there are two parts of the same process. Dissociation is the separating, solvation is the surrounding of the ion. Now we can show this in a chemical formula by simply writing the ionic compound as a solid, as a reactant, and then as the products, we simply write the ions and how many of those ions there are for that ionic compound. So this is how we will show the process of solvation of dissociation for sodium chloride. Sodium chloride solid becomes Na plus aqueous plus Sil minus aqueous. Because when sodium chloride becomes an aqueous solution, it actually separates into its ions through a process called dissociation. So those ions in water are going to be surrounded by water. So that sodium chloride lattice gets surrounded by water molecules because, again, as we said earlier, and we have a picture over here, water is going to be polar, with the oxygen being partially negative and the hydrogens being partially positive. So when water attacks the sodium chloride structure, crystal, and it removes the sodium ion, Na+, it gets surrounded, the sodium ion, with water, with the oxygens facing the Na+. Why? Because the oxygens are the negative part of the water molecule. And then the chloride ions, when they get solvated by water molecules, when they get surrounded by water molecules, the chloride ions get surrounded by the hydrogen part of water because those are the partial positive part of water. That is where the positive is. And that positive is attracted by the negative. Remember, opposites attract. It's magnetism. So when water gets attracted to the chloride ion, which is negative, it's going to be attracted with the hydrogens attracted to the negative. So in general, not just with sodium chloride, but with ions in general, water molecules are going to solvate the ions with water molecules surrounding the anion, and if you remember, that's a negative ion, with the partial positive hydrogens facing the chloride or the negative ion, the anion. And then water molecules are going to solvate the cations, they're going to surround the cations with the partially negative oxygen facing the positive ions. And this happens anytime an ionic compound is surrounded or is put into water and dissolves in water. This is why ionic compounds dissolve in water. It's not because of like dissolves like. Again, those ionic compounds do not have intermolecular forces. It's because the sodium ions, or the ions in general, are attracted by water, and so the crystal ionic compound dissociates into its individual ions. That is pretty much it for section 1. It is very short. We will do section 2 next class, but do remember to also watch that other video showing you how a supersaturated solution looks like. Thank you.